Push the buttons one at a time in order and count each push. That total is your answer. You get to choose how the letters are split up among keys 2 through 9, with each key getting its own distinct set of letters, and the trick is finding the split that adds up to the fewest total pushes for spelling out the word. Beginner level, let's start with something you've actually touched, an old phone keypad. On that keypad, key 2 always means ABC in that order no matter what. So if you want to type the letter C's, you have to press key 2 3 times, because it's the third letter on that key. That's wasteful if C shows up a lot in your word. Today's puzzle asks, what if we could design the keypad ourselves, deciding which letters go where? By the end of this video, you'll be able to design the keypad ourselves, deciding which letters go where. Before we touch any code, let's build intuition with something totally unrelated to phones, your spice rack. The sauce or spice you use every single day, you keep it right at the front, easy to grab. The weird jar you use twice a year goes on the top shelf, where it's a bit of a reach. That's the whole idea here. Give the easiest, cheapest spot to the thing you use most, and shove the rare stuff somewhere more expensive to get to. This exact idea also powers things like music file compression. Keep this spice rack picture in your head. Its basic idea also powers things like music file compression. Let's look at a simple example first. Say word equals effect. Notice something. A, B, C, D, and E each appear exactly one time, none of them repeat. Since we get to design the keypad ourselves, we can just give each letter its own key. So each one only needs a single press. 5 letters, 1 press each, so the answer is 5. Nothing tricky yet, this is just here. So we know what the answer even means before we deal with harder cases. Good news, we only need 4 small Python tools, and I'll explain each one with a tiny example before we use it for real. First, counter from Python's collections module. If you write counter up, you get back something like a dictionary that says A appeared 2 times and B appeared 1 time. It just counts things for you in one pass. Second, sorted 1 20. It just counts things for you in one pass. Second, sorted 1 5 3 and call sorted on it with reverse true. You get 5 3 1, biggest first instead of smallest first. Third, enumerate. If you loop over enumerate x z z z x step gives you a pair, the index like 0 1 2 and the value like x z's az's at the same time, so you don't have to track the position yourself. Fourth, the ACK operator, integer division, which just means divide and throw. Let's pin down the rules of this puzzle so we know exactly what we're working with. There are 8 usable keys, the number keys 2 through 9 on a phone. Each key can hold as many letters as we want. There's no limit per key. If a letter is the nth letter placed on a key, typing it costs n presses, so the first letter on a key costs 1 press, the second costs 2 presses, and so on. The word we're given can be as long as 100,000 characters. One more thing worth remembering, English only has 100,000 characters. One more thing worth remembering, English only has 26 letters placed on a key. Here's a trap it's easy to fall into, picturing a real phone keypad and just using that layout. On a real phone, key 2 always holds a BC. That mapping was chosen for finger reach, not for typing speed on any particular word. But this problem does not ask us to use the real layout. It lets us choose which letters go on which key and in what order. So if our word uses e's constantly and almost never, we're totally free to put eases in a cheap first slot and a somewhere expensive. Don't reach for the real keypad picture. It'll lead you to the wrong answer. Here's the core idea, and it directly matches our spice rack picture from earlier. First, count how many times each letter shows up in the word, that's its frequency. Then sort the letters from most frequent to least frequent. Now hand out the cheapest possible slot, cost 1 to the 8 most frequent letters, 1 letter per key since we have 8 keys. Only after all 8 keys already have 1 letter each do we start giving out the next slot, at cost 2, again 1 per key. I like to call this the frequency ladder. Each rung of 8 letters costs 1 more press than the rung below it. You might wonder, how do we know sorting by frequency is actually the best strategy and not just a reasonable guess? Here's a simple way to check it with real numbers. Suppose a letter that appears 10 times is sitting in an expensive cost 2 slot, while a letter that only appears 2 times is sitting in a cheap cost 1 slot. Let's just swap them, put the 10 in the cheap slot and the 2 in the expensive slot. Before the swap, 2 times 10 plus 1 times 2 equals 20. After the swap, 1 times 10 plus 2 times 2 equals 20. The total went down. Whenever letters are out of orders like this, swapping them to fix the order never makes things worse and usually makes them better. Let's make the frequency ladder idea really concrete. Once we've sorted letters from most frequent to least frequent, give each letter a rank. The first most frequent letter is rank 1, the 2nd is rank 2, and so on. Ranks 1 through 8 each cost 1 press, because that's the first round through our 8 keys. Ranks 9 through 16 each cost 2 presses, That's the second round. Ranks 17 through 24 cost 3 presses. And since English has only 26 letters, at most ranks 25 and 26 exist and they cost 4 presses. So the pattern is, every block of 8 letters costs 1. Let's carefully walk through a full example by hand. Say we have 9 distinct letters, and after sorting their frequencies from biggest to smallest we get 5, 4, 4, 3, 3, 2, 2, 1, 1. There are exactly 8 keys, so the first 8 of these letters, the ones with frequencies 5, 4, 4, 3, 3, 2, 2, 1, each land on their own key at cost 1. That uses up all 8 keys' first slots. The 9th letter, the last one, doesn't get a fresh key anymore. It has to go into a key that's already used as the second letter there, so it costs 2 presses. Let's add it all up. The first 8 letters contribute their frequency times 1 press each, which is 5 plus 4. Now let's translate what we just did by hand into actual code. Counterword walks through the whole word one time and hands us back how many times each letter appeared. Exactly like the tiny example from before, where counterarb told us a shows up twice. Freaktoad values then gives us just the counts themselves. We don't care which letter had which count anymore, only the numbers. Sorted arranges those counts from biggest to smallest, so the most common letters are lined up first. Exactly the order our frequency ladder node. Now we loop over our sorted counts using enumerate. Remember, enumerate hands us both the position I and the value C at each step. Here I starts at 0 for the first, most frequent count, I is 1 for the second, and so on. That's our rank. Just counting from 0 instead of 1. The cost for that rank is IHH plus 1. For I from 0 to 7, this is 0HH plus 1. For I from 8 to 7, this is 0HH plus 1 to H. 8. Wait, actually HH 1 2 and so on. Each time I crosses a multiple of 8, the cost goes up by 1. That's our ladder rungs from before, written as one small formula. We multiply each count C by its cost and add it to a running total. Let's trace the actual code on our 9-letter example from before. Frequency is 5004, 1000, 3000, 2001. So we can see every single number the code produces. Letter AZC0, so AZ0. So AZ8 is 0, cost is 1, contributing 5 times 1 pi CZZ, ACCCZZ. DEFGH is GD0. So cost stays G0, so cost stays 1, contributing their frequency times 1 each. Then letter A's lands at I8. 8 8's HCZ08. Now HC8 is 1, so cost becomes 1. So cost becomes 1 plus 1, 2, contributing 1 times 2. To add up every contribution, 5 plus 4 plus 4, 2 plus 4. Let's practice before moving on. Pause the video here if you want to try it yourself. The word is ABCAGD. First, figure out the frequency of each letter. How many times does A show up? How many times does AG? How many times does AG? How many times does E's? Then sort those counts from biggest to smallest and work out the cost for each one using what we just learned. Remember, there are only 3 distinct letters here, well under the 8 keys we have available. Add up frequency times cost for each letter to get the total. Give it a real try before you check the next slide. Let's check your work. In aabbc, AB is 2 times, ABC is 2 times, and CC is 1 time. Sorted from biggest to smallest, that's 2 to 1. We only have 3 distinct letters here, way fewer than our 8 available keys, so every single one of them fits in the first cheapest slot on its own key, meaning every one costs just 1 press. So the total is simply 2 plus 2 plus 1C. Let's flag 2 mistakes so you never make them. Mistake 1, sorting the counts in the normal, smallest to biggest order instead of reverse. True. If you do that, your most frequent letter, the one you want to be cheapest, ends up getting the most expensive slot instead, which is exactly backwards from what we want and gives a wrong too high answer. Mistake 2, and this one is sneaky, assuming the problem wants you to use the real phone keypad layout, A, B, C on key 2 and so on. It doesn't. We get to invent our own layout. That's the whole point of the problem. If your code ever assumes a fixed real-world mapping or sorts the wrong direction, go back and check those 2 spots first. A quick word on speed, so you know this solution is fast enough even for the longest allowed word. Counting every letter means looking at each character in the word exactly once. So that part takes time proportional to the word's length. We call that on. The sorting step only ever sorts at most 26 numbers, since English has only 26 letters, no matter how long the word is. Sorting a fixed small list like that is so fast it barely counts, so the whole solution runs in own time overall, meaning it scales directly with the word's length and stays fast even at 100,000 characters. Let's sanity check a few unusual inputs to build confidence in the solution. If the word is one letter repeated over and over, like there's only one distinct letter, so it gets rank 0, cost 1, and the total is just the word's length. If the word somehow uses all 26 letters of the alphabet, the two least frequent ones will land on rank 24 and 25, both costing 4 presses, the maximum this problem allows. And if the word is a single character, like the total is simply 1. In every case, the same small piece of code handles it correctly without any special casing. Let's recap the whole journey. Count how often each letter appears, sort those counts from most frequent to least frequent, and then each letter's cost is just its rank divided by 8 using integer division plus 1. That's the entire frequency ladder, from the spice rack idea all the way to working code. Remember that poor letter C's from the very start of the video stuck costing 3 presses on the old fixed keypad? Now you know exactly how to design a keypad where a rare letter never has to be expensive, unless it truly is rare in your word. If you followed along here, there's a simpler closely related problem worth trying next, where letters are ranked by the order they first appear, instead of rank spine row. Remember that poor letter C strands from the very start of the video, stuck costing 3 presses on the old fixed keypad. Now you know